behavior as is how many of you know what we're talking about when I say phase lag? Oh, I guess we're going to have to cover that a little bit. But no attenuation in high frequencies, such transport lag, normally exist in thermal, hydraulic, and pneumatic systems. Who knows anything about a thermal system? Raise your hand. Who knows anything about a hydraulic system? Raise your hand. Who knows anything about a pneumatic system? That means pressure. Raise your hand. So, guess what? Transport lags normally exist in these things. And you've discovered them. I mean, we had 4 presentations on T0. We call it dead time. Look at this. Oh, J omega. You know that's the same thing as S. Wherever you see a J omega, you can put an S in there to simplify it. All right. Look at this. You ever seen something like this? Here we have time on the x-axis, and here we have the control variable output. This is on the y-axis. This is a time versus, this is a output versus time graph, time domain. And apparently something happens at time t equals 0, and whatever this value, whatever this variable is, comes up here and studies that. You see anything like that? Yeah. This is like a step response. This, you draw a tangent to that, to where the steepest point. Does this sound familiar? And you come down to here, and that distance there he calls it L now. But it means dead time. L on this page, this is page 569. Page 569, L is dead time. So if you don't mind writing in your book, you can write equals dead time. T is the horizontal distance of where this tangent line at the inflection point. Inflection point's another name. You want something to drink? Inflection point is another name for the steepest slope. What's the difference between inflection point and steepest slope? Thank you. I'm not sure you're right, but we'll go with that. So where this crosses the original initial steady state value and where this crosses the final steady state value, and he calls that capital T, which we call tau. This is one way to get tau. It's different than what we talked about last week. We talked about going up 63.2%, coming over here and coming down here. Notice you get a different value. I wonder which one's right.
Are they the same just because it's been shifted over? Because that one takes into account for the L?
No, both of them start from L. The way we did it last week, we went from where this crossed out to some place where this reached 63.2%. They're different. Which one's right? You want me to answer? I'm not going to. And the reason you want those, here's the Ziegler-Nichols tuning rule. And we're going to use these in a few weeks. And you need to know the value of T and the value of L. And I'll give you the parameters of the controller. We haven't talked about the controller yet, much, or any, for all I know. go back to something else now. Let's go down here. This is week 4, so let's see what we're going to do in week 4. Weekly assignment schedule. Modeling first order plus dead time with Excel. Modeling with Excel. No experiments this week. So in case, just in case, someone in your team hasn't completed all of their weeks 1, 2, and 3 experiments, they can right now, today, tomorrow, and Friday, because there are no experiments in week 4 assignments. Week 4 is modeling. And you're going to learn how to model dynamic systems with Excel. You're going to observe the dynamic response of the mathematical model for a system, observe the impact of parameter values on the dynamic response, and learn how to obtain modeling results in a graphical and tabular form. Who's ever heard of the FOG factor? Has 2 G's on it, F-O-G-G factor. It's the number of words in a sentence plus the number of polysyllabic words in a sentence. So dynamic is a polysyllabic word. Response is mathematical is polysyllabic. Parameter is a polysyllabic. Graphical, modeling, a bunch of long words. If they're more than 14, if your FOG index is more than 14, it's too high a level language for most people. So that's why I broke that up into several short sentences. All right. Here's what you do. You're gonna use Excel. How many of you know how to use Excel? Raise your hand. Who doesn't? Raise your hand. Good. You're gonna learn a little bit more. We're gonna model a step response experiment. And we're going to find out what the model says is the gain, T0, and scratch that. We're not going to find out what the model says. We're just going to play. This week is just play. So you're going to, here's a time domain equation for the input. This is a unit step function, amplitude A. Here is the time response of the FOPDT system. You can get that by taking the Laplace transform of this and the Laplace transform of the transfer function for your system, multiply them together, and then do the inversion back in the time domain and get this. Is that sweet? You want to see me do that? Sure. I'm not going to do that. But I'll tell you the process. Shall I tell you the process? Laplace transform of this. This is the input into the system. Laplace transform of the system, multiply them together, and you get the Laplace transform of the output of the system. Am I doing that in the right direction for you? Yes. Input here, box, output. So in the Laplace domain, the input multiplied by the box gives you the output. Easy as pie. You with me, Alex? Huh?
I'm Dave.
Huh? I know that, but I'm pointing at Alex. You need to leave?
Soon.
David?
Yes, sir, soon.
Okay. You with me, Alex? You more or less?
More or less.
Okay, what questions do you have?
I got the input box equals the output.
That's in the Laplace domain, not the time domain. In the Laplace domain, you multiply things together. You know that. Now then, you know how to do the inversion into the time domain? You can say yes or no. Huh?
No.
Okay, that's all right. If you do the inversion in the time domain, this is what you get. Here's the answer. So now you know. You know what the answer is. You don't have to know how to do it. So We want Excel to draw a graph of these equations so that we can see the effect of these different parameters, because I don't know if I can enlarge that thing. Do you think I can enlarge that? Yeah. Notice that formula, it's a little bit hard to see. Where is it? It has T0 in here and T sub D. That's where the disturbance happens, where the step up happens. It has tau in here and it has K. So this is a model, Excel model, of what your step response looks like. So this week all I want you to do is do that. Here's a tutorial. Now this is a tutorial for the old Excel, like 97 version. If any of you want a little extra points, you can convert this to the 2003. A lot of it's the same, but some of it might be different. All you gotta do is follow these steps. And then I want you to draw a graph. This is where it gets specific for 97 Excel, because you don't have one of these things on your choose scatter plot. Have I told you that? Scatter plot? Always use scatter plot. Using parameters, and this is like naming things like TD. That's where the step occurs. Amplitude of the step. Gain T0 and tau. That's dead time and time constant. Repeat that. Look at it. Oh my! Look at all this. And then save your Excel file. Put it on the blackboard, your team color file exchange. And send me an email that says you've done it. You're going to use that file again next week. So this is just building a simple Excel program that has a graph on it. And that's all you need to do this week. Question? Caleb? Question, Nicholas? Question, tell me your name. Nathan. I knew it started with an N, but I couldn't get the rest of it. Question, Nathan?
No.
Oleg? You pronounce your name Oleg or Oleg?
Oleg.
Oleg. Where's that from?
Ukraine.
Ukraine. I know somebody named from Armenia has the same name, but he pronounces it Oleg.
You stole it.
Huh?
You stole it.